Good morning, students. Today we are going to see the Schrodinger time-dependent equation. You all know that the Schrodinger wave equation is used to describe the behavior of the particle or the change in the behavior of the particle over the time period. The time-dependent equation is to describe the behavior of the particle over the change of time and space. That's why it is called the time-dependent Schrodinger equation. When the wave is propagating along a medium, it makes the particle to oscillate about their mean position. The oscillation to and fro along the same path, we know it is referred as simple harmonic motion. The displacement due to the simple harmonic motion is described by the simple equation y is equal to a sine omega t minus kx. Here omega we know its angular frequency, which is given as 2 pi nu. Nu is the frequency. A is the amplitude of the wave and k is the propagation constant, which is given as 2 pi by lambda. Nu is further written as v by lambda. So substituting this value, the equation y is equal to a sine 2 pi is taken out as common term and is written as nu t minus x by lambda. Substituting the value of nu as v by lambda and taking out the term v outside, the equation further becomes a sine 2 pi v by lambda into t minus x by v. This particle describing simple harmonic motion, quantum mechanically associated with the matter wave, represented by the wave function psi of x comma t. We know that the wave function is not a measurable quantity directly and may be in complex in nature. So the wave function associated with a particle which moves along the positive x direction is represented as psi equal to a e power minus I omega into t minus x by v. Here a represents the amplitude of the oscillations, omega is the angular frequency, t is the time period, x is the position and v is the velocity. As we have already seen, omega is nothing but 2 pi nu and v is nu lambda. The above wave equation is modified as psi is equal to a e power minus I 2 pi nu. Omega இருக்கிற இடத்துல 2 pi nu we are substituting and within bracket we have t minus x by nu lambda. Where v was there, we are just substituting as nu lambda. Now we take the new term inside the bracket and then multiply and we get as a e power minus 2 pi. Within the bracket we have nu t minus nu x by nu lambda. Nu gets cancelled, so the second term just remains as x by lambda. If nu is the frequency of the oscillation, according to Planck's equation, we know the total energy is given by E is equal to h nu. Here h is the Planck's constant and h cross is nothing but h by 2 pi. Therefore, h is equal to, in terms of h cross, it is 2 pi h cross. Therefore, in equation 3, in the place of h, we are going to substitute 2 pi h cross. So, the energy equal to 2 pi h cross into nu. Thus, when we keep nu one side and bring out the rest of the term to the other side, nu becomes E by 2 pi h cross. Also, we know lambda according to de Broglie hypothesis h by p. Here h is written in terms of h cross, so 2 pi h cross by p. Now in the equation 2, we are going to substitute the values of nu and lambda as we have derived their expression in the previous slide. We are going to substitute in the equation 2, and the equation 2 becomes psi is equal to a e power minus I 2 pi et by 2 pi h cross minus xp by 2 pi h cross. We see within the bracket term, in the denominator, we have 2 pi h cross as common term. So therefore, that common term is taken out of the bracket and the equation is written as a e power minus I 2 pi by 2 pi h cross. Within bracket now we have et minus xp only. Then 2 pi in the numerator, 2 pi in the denominator get cancelled. So the psi equation becomes psi is equal to a e power minus I by h cross et minus xp. The equation just we have described as number 4 is giving us the mathematical representation of the particle which is moving with unrestricted force with the total energy E and momentum P along the positive x direction. In general, the total energy of the particle is written as the sum of kinetic energy and the potential energy. So E is equal to half mv squared, which is representing the kinetic energy term, and capital V, which is representing the potential term. Now, in the first term, kinetic energy term, we are going to multiply and divide by a m. Therefore, it becomes m squared v squared divided by 2m plus v. We know the momentum P is equal to m into v. Here m squared v squared is there, therefore it represents the momentum square, therefore P squared by 2m plus the potential energy term v. If we are going to multiply with the wave function term on either side, so that is psi, so it becomes equation 5, which is represented E psi is equal to P squared psi by 2m plus V psi. Here, as we all understand, potential energy is the function of x. Now we are going to differentiate equation 4 with respect to x. What was equation 4? It was psi equal to a e power minus I by h cross e into et minus xp. We are going to differentiate this equation with respect to x. Therefore, the equation becomes dou psi by dou x, which is equal to a e power minus I by h cross et minus px, and we are differentiating with respect to x, therefore ip by h cross. So this is the differentiated equation of equation number 4. Once again we are going to differentiate this equation in order to get dou squared psi by dou x squared. Therefore, this equation becomes minus p squared by h cross squared a e power minus I by h cross et minus px or xp. Now, from the above equation, a e power minus I by h cross et minus xp is nothing but psi according to equation number 4. Therefore, in that term, we are going to replace with the psi term. So the equation 6 becomes dou squared psi by dou x squared equal to minus p squared psi by h cross squared. Now we are taking h cross square, which is in the denominator, to the other side. So it becomes p squared psi by minus h cross squared dou squared psi by dou x squared. Now we are going to differentiate equation 4 with respect to time. So the equation 4 differentiated with respect to time becomes dou psi by dou t equal to a e power minus I by h cross et minus xp. We are differentiating with respect to time, therefore it is minus ie by h cross. A e power minus I by h cross into et minus xp is nothing but psi. Therefore, that term is replaced with the psi. Therefore, we get dou psi by dou t is equal to minus ie by h cross into psi. Now, we have the e psi alone one side and bring out the entire term, the rest of the terms to the other side. So it becomes e psi is equal to minus h cross by I dou psi by dou t. Now we are going to consider equation number 5. What is equation number 5? E psi is equal to p squared psi by 2m plus v psi. In this equation, we are going to substitute the values of p squared psi and e psi that we have just derived in the above slide and substitute in equation 5. So the equation 5 becomes minus h cross by I dou psi by dou t equal to minus h cross by 2m dou squared psi by dou x squared plus v psi. We are going to multiply the equation entirely by minus sign. Therefore, the equation 12 becomes h cross by I dou psi by dou t equal to h cross squared by 2m dou squared psi by dou x squared minus v psi. This equation number 13 is representing the time dependent Schrodinger equation in one dimension. We can also write the Schrodinger time dependent equation in 3 dimensions. How it is written? How h cross by I dou psi by dou t equal to h cross squared by 2m del squared psi minus v psi. What is del squared? You know that it is called as Laplacian operator, which is giving us the 3 coordinates, that is dou squared by dou x squared plus dou squared by dou y squared plus dou squared by dou z squared. Therefore, now the equation 14 represents the time dependent Schrodinger equation in 3 dimensions. Thus, the time dependent Schrodinger equation can be derived from wave mechanics considering the equation that is executing a simple harmonic motion.